Alrighty, so the rest of this unit on circular motion is going to concern vertical circles, or parts of circles. So if you're going over a bump in the road, that's like going in a circular motion, at least for the bump part. Or if the road has a dip in it, that's like going at the bottom of a circle in the road. Okay, and so or think of a roller coaster. A roller coaster has all kinds of loops, vertical loops, at least a couple vertical loops, so that you know what I mean when I talk about the forces at different points of the vertical circle. Okay, so we're used to the normal force, or I just call it capital N in a box. Normal force is usually equal to your weight. Normal force is the surface you're on pushing up on you. Okay, so as you sit in that chair, the chair is pushing up against you with a force equal to your weight. Your weight does not change. In a certain location, depending on how fast you go, your weight doesn't change. But if you're accelerating up or down, your scale reading, your weight, your apparent weight, as they call it, same thing as a scale reading or normal force. These are all synonymous: scale reading, apparent weight. That can change. So you feel heavier or lighter depending on how you're going over the curve. So if you meet a depression in the road as you're driving, you feel smushed at the bottom of that depression. You feel heavier than you would on a level road moving. Okay, so your apparent weight's greater than your actual weight. If you're going over the top of a hill, you feel lighter. The normal force is going to be less than the weight in that situation. In fact, if you go too fast, you'll fly right off the road. Okay, so this change in the normal force, this change in what you feel like you weigh, is going to be part of the explanation of vertical circles and centrifugal force. Okay, so these astronauts right here, or pilots, are training for that feeling of weightlessness that you get if you were orbiting the Earth. So how come they do not? They're in an airplane, and the airplane is falling with them. So this big airplane goes up high, and then it just drops. And as it drops, the airplane is dropping at the same rate. The airplane is dropping at the same rate that the people inside are dropping. Okay? So the airplane is no longer pushing up against the person that's standing in it or sitting in it. So there's no normal force. So the parent weight is weightless. It's not really, actually, the actual weight does not even change. The astronaut has weight and the airplane has weight. But because they're both falling at the same rate, free fall, everyone in the airplane feels like, hey, the airplane's not pushing up against me. I have no weight. I feel weightless. But again, their weight is there. But their apparent weight is 0. Now, this is what astronauts do in the International Space Station when they're orbiting the Earth. They are falling. The space station is falling. It's also going forward very fast because the rocket that sent it up there. So it's falling towards the Earth. But it's going so fast forward that it never meets the Earth. It stays in its orbit at that certain speed. We'll talk about that later when we talk about gravity. But the occupants of that International Space Station are feeling weightless because they're falling with the International Space Station constantly. But they still have weight. They're not that far up off the ground that their weight is influenced, that their actual weight is that much different than when they're on the Earth's surface. So if we were to draw the free body diagram of a car going over the top of a hill, it would look like this, like we did before. There's the car. The normal force would be less than the force of weight, because the centrifugal acceleration would be downward. I don't really draw that on my free body diagram, but I will. It's a different color. So the acceleration is downward, and actually that centrifugal acceleration, keeping it in the circle. The v velocity is tangential, so I'll draw it like that, even though that's not really part of the free body diagram either. The black is the free body diagram. You just draw the forces, right? This is supposed to be W for the weight. Okay, so we can see that the net force would be, in this case, the weight minus the normal force. The weight has to be bigger in this case. The centrifugal force is always in the same direction as the centrifugal acceleration, which is downward. So the weight has to be bigger than the normal force, and because they're opposing each other, you got to subtract them. And so you subtract the smaller one from the bigger one. The bigger one's always the one that's pointing towards the center of the circle in vertical circle problems. So here's what I just explained on the previous page, except I'm drawing the centrifugal force over here towards the center. If I use Newton's second law, Fc equals net force equals MAC. And Fc in this case would be the bigger one minus the normal force equals MAC. And very important to realize that Net force and acceleration always point to the center of the circle. And net force is the difference, if the forces are opposite each other as they are here, in the weight and the normal force. Okay. So once again, Fc equals, in this case, the bigger force minus the smaller force, W minus N, which would also equal MAC. Supposed to be a subtraction sign there. Now, we're going to do it at the apparent weight, which is also called the normal force, in terms of mass, speed, and radius. Okay. Well, first of all, weight, which is mg minus normal force. Okay. Normal force is the apparent weight. That's what we're trying to solve for. In terms of mass, speed, and radius, well, that equals centrifugal force. And centrifugal force equals m tangential speed v squared over radius, because that's what Fc equals. So if we're going to solve for n, let's add n to both sides. Let's add n to both sides. So we don't need this anymore because I put it in terms of mv squared over r. So let's add n to both sides. So mg equals n plus mv squared over r. And then let's cross out. Let's get n by himself because that's what I'm trying to solve for. What would the scale read as I fly over this hill? So n equals mg minus mv squared over r equals m times g minus v squared over r if you want. Okay, so I could figure out what the scale reading is using that equation. Now, the faster you go over this hill, the smaller the normal force becomes. As V increases, at least on the top, we're talking about the top of a vertical circle. As V increases, the normal force decreases, because if you go too fast, you'll just fly off, because there is no normal force if you go too fast. So this happens at the top, but weight doesn't change. Your actual weight, when I say the apparent weight decreases, the weight stays the same. But what you feel, the seat pushing up against you, decreases until you come off the seat if you go too fast. Your whole car comes off the road if you go too fast. Okay, so the apparent weight depends on the motion, how fast you're going. Okay, so if I were to ask you to solve for the velocity at which object would become weightless, well, let's use our equation. So Fc equals equals the bigger one, the true weight minus the normal force. So mv squared over r is what Fc is, equals mg minus n. So if I was going so fast that the normal force was 0, what's the minimum speed I could take before I go airborne off my seat? So that'd be n is 0. And this would be the maximum speed I could go if n equals 0. Okay, so that'd be the minimum speed to stay in your seat. To stay in your seat, but you wouldn't feel the seat. Or stay on the road. Crest. Top, near the top. So, let's just work this out. mv squared over r equals mg, because n is 0, and the m's cancel out. We get something that looks familiar. Velocity equals the square root of the radius times the acceleration due to gravity, which is 10. Okay? So I just derived an equation for the maximum safe speed you can take a hill without flying off. Actually, the minimum safe speed the minimum speed you can take the hill before you fly off. You go any faster than this speed, and you'll be flying off. You won't have enough centrifugal force to keep on going around the top. Okay, so just review that. If n is 0, the only net force on you is the weight, or I guess what I meant is the weight, which is mg, since Fc equals mv squared r. Fc is equal to mg, the m's cancel out, and we're left with v squared equals rg, or v equals the radius times the acceleration due to gravity. So all this is saying that past that speed, if you exceed that speed right there, the car will not stay on the road. You will not stay in your seat, and the car will fly off and will go airborne. Now, what if you drive through a dip in the road? Okay, a little valley in the road. We're at the bottom of a vertical circle then. Okay, so the road might have gone like this. Okay? So, the centrifugal acceleration is pointing upwards, as you can see by the green arrow. That means the force, there has to be a centrifugal force acting upwards, because centrifugal force causes the acceleration. So if I were to draw a free body diagram of that car, I don't ever draw the net force. Okay, I don't draw the net force. So here's the car. Here's the weight of the car. That doesn't change, like I said before. But since the net force is upward, the normal force, the car seat pushing up against you, or the road pushing against the car, the normal force, the apparent weight, it has to be greater than the downward weight. Why? Because you have to have a centrifugal force that is pointing upwards when you're at the bottom, or else the car won't keep on going around the circle. I'll go off on a tangent. So FC is equal to the upward force minus the downward force. So if you remember, at the top of a hill, you have to have, okay, you have the weight, then the normal force is up here. The normal force has to be less than the weight. I mean, it's less than the weight when you're at the top of the hill as opposed to the bottom of the hill. Like we talked about before. And so this is because FC has to be downward, so the weight has to be bigger than the normal force. Okay, notice the difference. All I did was switch around the mg and the n. Okay, notice that difference right there. So the FC at the top compared to the FC at the bottom. Okay, at the top compared to the FC at the bottom. Okay, in a roller coaster, you can feel you're smushed at the bottom, whereas at the top you feel like you're flying out of your seat. Top of a vertical circle, that is. Okay, so like I said, here's a free body diagram. Right here, circled in green. Y at the bottom circle is n greater than the parent weight, greater than the weight, is because you need a force pointing towards the center circle to keep the car moving around this vertical circle. And these two forces are opposing each other. So net force equals a bigger force, which better be the normal force minus the weight. Okay, making that picture in green there. Why? I don't know why they had the acceleration like right here. The acceleration should be upward. So that was a mistake. Acceleration is upward. So the net force also is, or the FC is also upward, as is shown in the picture. So once again, I don't know why they did that. The acceleration is upward. They made a mistake. So acceleration is upward towards the center of the circle, as is shown right there. So the net force has to be upward. And so, actually, I'm deriving that equation that I already have there. How did I get it? FC is equal to normal force, the bigger one, minus the W. FC is mv squared over r equals n minus mg. So if you're solving for your scale reading, it'd be mv squared over r plus mg, as I drew right here. Now, this is totally different. These, for the top of the circle, okay, well, anyway. Okay, if you're at the top of the circle, it's totally different. And we can look back and see that for the top of the circle, which we already talked about, would equal mg minus the centripetal force. Okay, so notice the difference. This be at the top of the circle on the left. Oops, we're talking about the bottom of the circle. For the left side, we're talking about the top of the circle. Right there, so distinguish between those. So I can, at the bottom of the road, at the bottom of the circle, as V increases, what happens, as speed increases, what happens to your apparent weight? You feel more and more smushed. Now, there's not, if you go faster and faster, it's not like you're gonna, fly off the road. In fact, you're gonna get smushed in the road. In fact, as you go faster and faster, the car scrapes its bottom against the road. In this way, at the end of a speed bump, you can see all these gouges in the road from cars that flew over, and then because for every speed bump, there's a dip after it. And the road's all carved up and scarred out from cars going too fast and bottoming out. So here they just distributed the mass out of the equation. Instead, I just showed you. Okay. Okay, this is the top of a hill. The passengers will have what appeared driving at the same speed on a flat road. Well, you feel lighter, so a lower apparent weight, which is the same thing as normal force. Okay, occupancy are trying to speed at 25. Okay, so that's V. Note that their apparent weight is 20% higher than their weight when driving at 25 on a flat road. Okay, so what we can say is 120% higher is like 1.2, or 120% of what you were. 20% of what you were plus 100%. So that'd be like 20% is 0.2. So that'd be 1.2, your normal weight, your actual weight. That's what your normal force feels like. Okay, so anyway, I don't have to solve this. I don't have to solve this. Me seeing that the normal force is greater than weight tells me that I'm flipping, I'm moving through the bottom of a circle because I need the upward force, in this case the normal force, to be greater than the weight, so I have a net force pointing towards the center. So it'd be a dip. So remember that equation, which I won't derive again. But when my velocity equals RG right here, that's when I'll feel no apparent weight. Okay, now we're getting into the type of problems that are utilizing what I just talked about rather than just conceptual. Okay, so here's the V, here's the R, There's the mass of the driver. What is the apparent weight? That's the normal force of the driver at the top of the hill. So I look at this. This is the top of the hill. So my equation is FC. Centrifugal force has to be downward. Okay. So that's the net force, centrifugal force. And so the weight better be bigger than the normal force. So that when you subtract them, you get the centrifugal force, the net force, which would be pointing downwards. Okay, so FC equals mg minus the normal force. I'm looking for the normal force. FC is mv squared over r. So add n to both sides equals mg minus mv squared over r. So I can just take out the m and plug your values in. Okay, so 60 times 10 minus 20 squared over 80 for radius. That is the normal force in newtons. I get 300 newtons. They're using 9.8. That's why they're getting 290. Now, when you're going over the hill, the radius is 80 meters. Okay, so what velocity, what minimum velocity, they should say, because you can go past it. So what minimum velocity must the car drive over a hill if they're to feel weightless? So that means n equals 0. That means only force acting on the car at the top would be the weight, because normal force equals 0. Centrifugal force would equal the weight. So mv squared over r equals mg, and I don't have to derive the equation again. Rg equals v squared. V equals square root of Rg. I could just plug directly in the equation. Okay, so the radius 80 times the speed. 80 times acceleration due to gravity. And I get 28 meters per second. So that's what they got to. Okay, so this is at the bottom of a circle. And the plane's, so the weight of the plane, of the pilot, is downwards. And the normal force is upward. But the normal force better be greater than the weight. So that's, when you get centrifugal force, is pointing upwards. So n has to be bigger when you subtract the two to have the net force being pointing upwards. Net force is the same thing as normal force, remember. Okay, so normal force is the apparent weight. It has to be greater than the actual weight. Okay, mg is the weight, right? So n has to be greater than the weight. Now, if you're in a roller coaster and you're upside down below the track, there's two forces acting on you if you're going fast enough. There is Let's draw a free body diagram. There's a roller coaster. You got the normal force, because, I'm sorry, let's do it easy at first. You got the weight of the cart pointing down. Now, if you're going fast enough, you're smushed against that seat if you're going fast enough. And you also have the normal force, but this is weird. The normal force is the seat pushing up against you, but you're upside down. So when the seat's pushing up against you, it's pushing downwards from our point of view here. So the centripetal force, or the net force, is adding these two, the parent weight plus your weight. Now, if you go faster, as the speed increases, the normal force would increase. Now, you can go too slow, then fall out. Okay, if you go too slow, you'll fall out of that cart against your restraint harness. Okay, but we'll do a problem with that in a second. Okay, sorry, I forgot to push a button, so let me walk through this. Okay, on the left is the new case, right here, upside down, top. And we can't experience that in our car, but on a roller coaster we can. Upside down, below the track, going over the top, under the top of a vertical loop. And right here we talked about this on the right. This is upright. Upright at the top, like we usually experience in our car, going over a crest in the road. Okay, so the difference is, let's look at the old one. The weight has to be bigger than the normal force to keep you going around the circle. So the centripetal force is equal to, subtract those, the bigger one minus the smaller one, weight minus normal force. As you go faster at the top of the hill, when you're upright, the normal force decreases. Let's go to the new one, upside down. When you're upside down, the normal force is pointing down if you have it. Normal force, if you're going fast enough, normal force plus the weight, because they both go in the same direction, is equal to the centripetal force, as I showed in this box. But as you go faster, the normal force will increase. Okay, so I just did this. Driving equation that relates the normal force to the speed, mass, and radius. Okay, so I kind of just did it. N plus weight is the centripetal force. Centripetal force is mv squared over r, regardless of the condition, whatever situation that's true. N plus mg, that's what weight is. Okay, so normal force is equal to mv squared over r minus mg. I could take out the m if you want. I mean, take it out of parentheses, but no need. Okay, find the minimum safe speed that you could go without falling out of a seat. So remember, as v decreases, the normal force decreases, at least at the top of the hill, like we are here, upside down at the top of the hill. Okay, so let's say the minimum safe speed is when n is 0. You're at the v minimum to be safe. So let's use this equation that I just derived up here. So n is 0. So I'm using this equation. 0 equals mv squared minus mg. So 0 equals m times v squared. Okay, so I'm just plugging into this equation right here. And there's 0 at the minimum safe speed. Okay, so basically we have mv squared over r equals mg. And the m's cancel out. And we're again stuck with this equation. V squared equals rg. And then v equals the square root of rg. So it's the same kind of feeling of doing the other problem where you got the maximum safe speed. The minimum safe speed at the bottom would be, what's the radius? So if I'm doing the other problem, so I don't have values to plug in there, but if I did, I just put in the r and the g, take the square root of the product. Okay, this is just a summary. As v increases, what happens to the parent weight, which is a normal force? Normal force would decrease. Right here, as v increases, the normal force would increase. Right here at the bottom, as v increases, the normal force would also increase. Okay, as we said before, just summarizing. Okay, so we're talking about a ball and a string at the top of the circle. Now there's no normal force if you're a ball on a string. Okay, instead of normal force, there is tension. There's tension in the string pulling it back so it doesn't go off on a tangent. Draw a free body diagram. Okay, so here we go. Here's the ball. Don't forget the weight. The weight is pointing down. And there's also tension pulling it back. So those two forces, and where's the acceleration? Acceleration is downward towards the center of the circle. So the equation to determine the tension in a string. Okay, so the relationship is centripetal force is the sum of those two forces, the weight plus the tension. So centripetal force is mv squared over r equals weight is mg and tension is what we're solving for. So tension equals mv squared over r minus mg, or m, take the m out. So solve the equation for tension. Tension equals the mass in point, using these values up here. That's mass. Then velocity is 2.5 meters per second squared over the radius, 0.4 minus 10, which is what g is. I calculated it out to be 2.8 newtons. So here is like a rock or a bucket of water. and it's at the bottom of the vertical circle. So we got tension pointing that way, but we have the weight pointing this way. And of course, which one has to be bigger of the two? It has to be the one pointing towards the center, so that you have an unbalanced or net force pointing towards the center called the centripetal force. So T has to be bigger than the weight at the bottom of the circle. Again, T is just like normal force, but it's tension in the strength. Same equation. So when the bucket's moving at the bottom of the circle, what is T? Okay, so in this case, FC equals, who's bigger? The tension minus the smaller weight. So FC is mv squared over r. Then I'm going to add the weight to the other side plus the weight. So T is equal to mg plus mv squared over r. And so let's plug in numbers. 2.5. G is 10 plus the speed. 3.5 squared over the radius, 0.8. It looks like I get 63.3 newtons for the tension. On this one, tension's pointing down, the weight's pointing down, and so centripetal force is the tension plus the weight. So mv squared over r equals the tension plus mg. So tension equals mv squared over r minus mg. So v squared over r minus g. So I plug in the values right there. And I get 13.3 newtons. The closest answer is 14. They're using 9.8, I guess, or they made a mistake. I don't know. That's how you do it. This one, looking at the water inside the bucket. So there is a normal force of the bucket against the water, and there's the weight of the water. So this is just like a car going in a Ferris wheel. I'm sorry, in a roller coaster. It's like one of the carts going upside down at the top of the roller coaster. What's the minimum velocity at the top of the circle for the water to stay in the bucket? Okay, we did this before. V equals RG. So without going through all that again, without deriving it, 0.8 times 10. So the square root of 8 is 2.82 meters per second. So this one's identical with different numbers, so I'm going to skip it. Okay, for this one, we're at the bottom of the loops. We got normal force pointing up. We got the weight pointing down. And you should know by now that FC is equal to the bigger one minus the smaller one. Bigger one has to be the one that points towards the center, which would be N. We're looking for N, so the apparent weight. So that'd be FC plus W. So that'd be mv squared over R plus G, like we've done before. Okay, so the mass is 500 v squared, 20 squared over the radius, 20 plus 10. So I can do this shortcut, 30 times 500. So that'd be 15,000 newtons. Just kept feeling smushed. So at the top of the loop, assuming he's not going too slow, we got normal force, we got weight pointing down. So therefore, the net force, centrifugal force, equals normal force plus weight. I'm looking for normal force. Normal force equals Fc plus weight. So that's m times v squared over r plus mg. Take out the m's. So we got 500 times 20 squared over 20 plus 10. So we're going to clean this up. 20 plus 10 is 30. So we're going to get 30 times 500, which is 1,500. What? 30 times 5 is 1,500. Is 15,000, sorry. Okay, obviously I made a mistake. And I was going so fast. So you shouldn't do that. So look, the math. N, right here. N equals Fc minus the weight. And so that would be a negative sign right here. And so there would be a negative sign right here. So 20 minus 10, so it only comes out to 5,000 newtons. Sorry. So they used 9.8, so they got a little more. Okay, when they have minimum speed, that's really easy. V equals square root of RG. R is 20. You don't need the mass. It doesn't matter. Times 10. So you get 14.1 meters per second. Okay, so this is different. They're asking for a centrifugal acceleration at the top when minimum value. Okay, so that would be when there's just the weight pointing down, because the normal force would be 0. Weight equals mg. So Fc equals weight. I'll show you this. mv squared over r equals mg. The m's cancel out. I don't really have to do this. I'm going along solving for v. They're not asking for v. Okay, so if your weight is the only force pointing down, you should realize that Fc equals MAC. Looking for AC. So Fc is equal to the weight. mg equals mac. M's cancel out. And so AC is equal to G, and of course is downward. So you gotta realize that FC is equal to the weight, because the normal force is 0. And the weight is equal to mg, and FC is generically, the generic equation in all cases, FC equals MAC. I put mg in for there, and that equals MAC, the m's cancel out. So AC is simply equal to G. Okay, and then finally, minimum value. Okay, at the top of the loop, we already know that equation without deriving it. So that would be this equation right here.